So we're going to find three ways to write this as a definite integral. We're going to start with the obvious, and then we're going to realize that on a multiple choice, knowing the AP, they could give you something a little less obvious. Okay? The idea is as follows. If I have the area between 2 points, there's probably an obvious one that comes out of here. But the area would stay the same if I did a horizontal shift to the left or to the right. Right? If I have area under a curve from 3 to 7, and I move that whole graph 2 to the right, and then do the area from 5 to 9, the area is going to stay the same. So that can be confusing because there's an obvious way to go about these. Okay? The obvious way here is saying A is 4. Because every single time we have done A plus change in X times I, in this case, it's K. That's what we've done every single time. We've done a starting point, and then we add our change in X a certain amount of times. So an obvious starting point would be A is 4. Well, from there, since the change of X looks like 6 is the distance, it would mean that your B value would be 6 to the right, which would be 10. Then you would get your X value to be 4 plus change in X times K, which would be 4 plus 6 over N times K, which matches up perfectly here. And we have the integral from 4 to 10 of X squared. This is what everybody wants to happen when they do these questions, because this is the obvious and logical way to go about it. But if all of a sudden you're in a multiple choice section and the obvious one isn't one of the choices, right? You're allowed to swear under your breath a little bit. And then take a deep breath and say, okay, what are some other possibilities? We could think of starting at a different spot. Let's start at 0. I still have my 6 over n, so my change of x still looks like 6 over n. So then my b would be 6. And then if I do a plus change of x times k, I just get 6k over n. And that is now my x value. What does that do to my definite integral? Now when I plug it in, I've shifted things 4 to the left. Can you see if you took your original one here, from 4 to 10 of x squared, if you shifted it 4 to the left, you would have an x plus 4 inside the function. And then your range that you're looking at is now from 0 to 6 instead of 4 to 10. The idea here, though, is technically you can choose any a value you want, any starting point. We almost always look in here, if there's a number plus something, that's the most obvious. A second one that's used often is 0, because it's kind of nice to start with an area from 0 to something. But when we start with that 0, and we still do a plus the change of x times k, we get just k, 6k over n. That's what our x has to substitute in for. And in our equation, that's just the 1 part and the 4 stays. Okay? A third way. You could decide to take this 6, because it's just a number, and factor it out in front. Now my limit, as k goes to 1 over n, has a 1 over n instead of a 6 over n. Again, I can choose any a value. I'm going to start at 0. But now my b value, if I had 1 over n, my b value is going to be a 1. From here, I get my a plus change of x times k, and I figure out that my x is k over n. So when I go to my formula and I substitute in, this 6 is still factored out. My starting value was 0, I went up to n, and then I have 4 plus 6x squared dx. That just wouldn't be nice if they gave that as the answer for the multiple choice. There was nothing, right, in the original, there was nothing that made me feel like I should go from 0 to 1. And then I could put that 6 back in afterwards if I wanted to. So now let's pretend this question was multiple choice. Okay? Let's pretend this question was multiple choice and you did as you normally would and you got this one, but it was not an option. How do we use the multiple choice to help us figure out what the option is? Okay? So, for example, if you're like, okay, I normally start these questions by solving it the way that I want to, and I got from 4 to 10 of x squared, and I felt really confident, but it wasn't one of my choices. So let's say the blue box was one of your choices. How do you check it? How do you see if it's one of the ones that could have been right? Because you went directly and found a great answer, and then the APA multiple choice committee decided to be not nice. So we look at the second one, okay? If you're looking at the second one, you always know that's your A value. And going from 0 to 6, you would know that your change in x would be 6 over n. Because whatever distance that's on top of here, whatever distance is on your integral, that's going to be your change of x divided by your number of integrals. So with that, you would have a, you would have change of x, and then you would be able to figure out UK by saying, I know that that's what would have to be substituted in for x. I then go and substitute that in for x and realize, oh, this one actually worked. But that's how you would use your multiple choice answer as a way to check. Because we found 3 here, 3 very different ones. Could you guess there might be an infinite amount of ways you could do this as a result? Yes. So it is not a good option just to start finding, oh, that one didn't work. I'll try another one at random, and then hopefully by randomly trying an infinite amount of them, eventually I find the right one. That's not a good strategy, right? I think it is a good strategy to do the normal one first, because most likely they'll be checking if you know the normal one, right? Because it changes. The normal one means this is a 3-minute multiple choice. A check each of the ones to see which one works makes it a 12-minute multiple choice question. It's much longer. But they'll do that sometimes. So, same thing with this last one. Okay? This last one tells me my change in x has to be 1 over n. In order to get that 1 over n in my original equation, I have to bring that 6 out. Next, I'd see that A is 1, A is 0, sorry. Starting point is at 0. And from there, I could find 0 plus, so I'd get k over n as my x value, and I'd be able to say, based in here, there's my k over n, that's what gets replaced with x. So I spent some extra time on this question because I really feel it gives us an idea of getting used to the format of these Riemann sums and then seeing it in different ways. Okay, it's a little frustrating that it can happen in different ways. We really like math that, right, as students, we like math that there's one way to do it and we know how to do it. That's our favorite math. These math questions were like, did you know there's 80 different ways you could do this? Yeah, feel free to choose whichever one you want. There's also 100 ways to do it wrong. Those are not the fun ones. Because you don't really feel confident. So you study one really well, and then you say, okay, but that's not the one we're going to put on the test. I'm like, oh. So, express the following Riemann sum as an integral. Okay. If I was doing it the easy way, it's got 2 plus. I definitely would pick A as 2. I see the 7 over n. I definitely choose my b value to be 9. And my change of x is 7 over n. This is what I would recommend, because then a plus your change of x times k, that substitutes in for your x. Life is easy. It's kind of interesting just talking through things when we have the definite integral and we're talking about reading it. This is the definite integral, or we would say this is the integral from 2 to 9 of x squared dx. And this dx part in the integral means that you are finding integral with respect to x. But a dx also means a small change in x. And in our summation formula, that's our change in x. So we notice that this blue part, that all got replaced with the x. The squared stayed. The green part gets replaced in the integration by saying a change of x in the integration formula too. So it's kind of neat to see how those things are connected. Of course, we could have decided 0. If you decided 0, then b value would be 7, because your change in x is 7. And now your x is 7 over nk, so this would have also been a correct answer. Right? And if we wanted to be, if I just wanted to make you guys struggle with mental math, I would say I'd like you to do this one. I'd like your a value to be 13/5. And I'd like your change of x to be 23 over 8. It's possible you would not like it, because you'd have fractions for 1, but then you would have to like factor out a 23 over, you'd have to make sure this stays as 23 over 8. So what would you factor out as 7? Oh, not nice. Okay. Good news is I've never seen one that not nice. My head said if I was creative and gave you the worst thing possible, that's what I think I'd do. And then I don't do it to you. Just imagine doing it. I have an evil little streak. Oh, now, assuming the lower limit is 0, So our a value is 0. We want a definite integral that represents all of this. Notice it's not in summation notation. It's expanded to give you the entire sum. Here's our change of x. Our change of x is out front. That's the width of all those rectangles. And these are all of the different heights. So question, can we write this in summation notation? What's changing? What's staying the same? Okay. This last one kind of gives you the formula. If you had put one in the middle, a kth one, what would it look like? Do you agree that they all have the 1 on the top? Do you agree that they all have a plus 3? Do you agree that they all have something over n? The first one has 2. The second one has 4. The third one has 6. The nth one has 2n. Could you believe that the kth one would have 2k? I think, did I use, I'm just gonna, oh, I used I. So I'm gonna do a quick erase. You don't have to erase this, but that would be the ith one. I just replaced the k with the I. Then my summation notation would look like this. I'm going from I equals 1 to n. I still have my change in x, 2 over n. And that 2 over n technically could be out in front, but it can be in there as well. And now I replace all of those sums with this. I've got a starting value that a is 0. And since my change of x is 2 over n, my b value will be 2. And my x value then is 2I over n. I now can write my integral. Goes from 0 to 2. I replace the 2I over n with my x, and I get my integral from 0 to 2 of 1 over x plus 3 dx. So I'd like you to try this next one on your own. Put up the answers for the first one so you can check how you did, and then you can try the second one there. All right, and here is the second one. So I have a 1 over n to the 4 here. And our change of x is always something over n. So see how I broke up that n over 4 to be 1 over n and a 1 over n cubed? That 1 over n cubed could get distributed to each one of those. And then my summation looks like that. So we're going to compute the following definite integral by writing the integral as a limit of a Riemann sum. So we have the interval from 1 over 3 into subintervals. So your change of x is going to be 2 over n. And your ui, if your starting point is 1, then 1 plus change of x times I, that's your x. And so we take this and say we have to add up all of our rectangles. All of our rectangles are all of the heights times all of the widths. And this part right here, that's going to go in where your x is. So we get 12 minus 1 plus 2i over n squared times change of x. And we reread the question and just said, oh, it said compute. Don't like the sound of that. It means we're not done by just writing the Riemann sum. So I multiplied this out by squaring it. And now I'm going to work with the math to try to get those formulas for I that I had before. I distributed the 2 over n inside. That gives me 3 different sums. And in each of those sums, I could do them each separately. And for each of them, I'm going to factor out all of the numbers and all of the n's, leaving just the i's, and in the first one, leaving just a 1. Do we remember the formulas for these 3? No, that's okay. I think you should remember the first one. What is adding up I to n of all the different ones? That'll just be n. The second one, that formula was n times n plus 1 divided by 2. The third one also has an n plus 1, but it also has a 2n plus 1 divided by 6. We still have some math to do. We can simplify though. The n's here nicely cancel out. One of these n's on top would, those ones cancel out. One n here, would cancel out with one n there. One n here, cancels out with one n there, leaving me with 2. So that's the first thing I could do to simplify. And I could multiply this out, which I've done there, to be 8n squared plus 12n plus 4. So what do I have? I have 22. If I multiply this out, negative 4n minus 4, I'd have negative 4n over n, negative 4 over n. And then multiplying this out and putting them all over 3n squared. Again, we could have some canceling here. Those would cancel. Those would cancel. One of these would cancel with one of those. And simplifying it right down would give me 62 over 3 plus 4 over 3n squared. The definite integral is the limit as n goes to infinity of the Riemann sum, and we simplified the Riemann sum to be 62 over 3 plus 4 over 3n squared. Of course, if you plug in n as infinity, that 4 over 3n squared will be 0. And our final sum is 62 over 3. And just like the definition of the derivative, we're going to be able to do this much, much, much easier. So much easier that I don't think they'll ever ask you to do this long way on an exam. But we still need to see, we have to get a little bit dirty and muddy to see, okay, this is the idea, and someone's going to find a much nicer way to do this. That's going to be awesome. That's where we're going to start a little bit. Well, not tomorrow. Tomorrow we've got more work on this stuff as an activity. But the fundamental theorem of calculus, starting tomorrow, gives us the shortcuts that we've been waiting for. I handed out your second